Hello, in this video I will explain you how you calculate a U-value for external wall where you have a cold bridge. And you can see I have the drawing of the wall here, where I have a cross section of the wall, where I show the two different kind of wall types I have. I have the main wall where I have a lot of insulation, and then above the window and at the side of the window I have a cold bridge where I have less insulation. So the formula that we're going to use here is the formula that we have for construction with cold bridges. So what we have to find is to find the final U-value for the construction is that we need to use this formula here, U-wall I'll call it. And that would be U1, the main construction, times the area of it, plus U2, the cold bridge U-value times the area of the cold bridge, plus the linear loss, psi k, times the length of it, divided by the total area, A1 plus A2. So what I have is, I'm going first to calculate the U-value, which is the main construction here, then U2 that I have going out here, U2, and then I have the linear loss in between, where I have a lot of insulation and then less the psi k. So these I'm first going to find, and then the areas, and then after that the length of the linear loss to be able to calculate the final U-value. So we'll go to the tables that we have to calculate the U-values. So jump to U1 here, and first I want to draw up the construction here. So I have here the brick on the outside, and then I have the light clinker blocks on the inside, and I have the insulation in between. So that was 110 millimeters, insulation was 190, and it was 108. So what we have is that we have the heat flow coming horizontal. So we'll cross up here horizontal. So the first we'll meet is the RSI, so 0.13. Then the next part we have is the light clinker concrete. And that had a density of 600. We need to go to DS 418 to find the lambda value. And we have the lambda values as shown in Annex F. We have them here. And I can only emphasize that you print out the table of contents so you can mark where the different things is in DS 418, so you can find your way around in DS 418. So we need to go to page 79, and then we need to go down to the graphs. And here we have light clinker concrete, and we have 600 in density that's given in the assignment. And then I have to see which curve, be it internal blocks and plates with glued joints, or we can have internal blocks. I think we'll be in curve A because it's elements. So go up here, and then we'll go over here, and we can see it's approximately 0.17. So go back and write that the lambda value is 0.17, and the thickness of the element was 0.14. 0.11. And then we have the R, and the R is D divided by lambda. So that is 0.647. Then the next we have is insulation. And the insulation is in thickness 0.19. And in the assignment it says that the lambda value is 0.036. And then the resistance is 5.28. And then we have bricks, and they have a density of 1600 kilo per cubic meter, and they have a dimension of 0.108. And then we need to go and look up the lambda value for it. We need to go to the graph here, and we can see it's curve B, external wall brickwork, 1600, and then we go over to here and it's 0.63. So 0.63, and then again the R is D divided by lambda, so 0.171. And then the last thing we need is the surface resistance from the outside, so 0.04. And then we add all these together, and that gives 6.268. And then the U value is 1 over R, so 1 over 6.268, and that would be 0.159. And then we need to, this is the uncorrected U value. Now we need to correct the U value, and we correct for air gaps. And to find out which level our wall is in, we need to go to DS 418. And this is under Annex A on page 60. Here we have these examples where we can see level 0, level 1, and level 2. And now we are here, soft insulation in a cavity wall with cavity ties, which is again a planned surface on the warm side. And as we have elements which are glued together, we have a planned surface. So we are not down here where we have soft insulation in a cavity wall with cavity ties, which is against brickwork. That's not where we are. And we're not either down here where we have insulation in a cavity wall with cavity ties and brickwork where we have unfilled and overfilled joints. So we are in level 0. So we go back and we can cross that here. And that gives us that delta U dot dot is 0.00. So that means that when we calculate this, it will give 0. But now I'll just fill it out so you can see where we get the numbers from. So we have R insulation, that's 5.28. And then we have the total R value, that is 6.268. And that, of course, we give 0 because it's multiplied with 0. And then we have the wall ties, and that's also given in the assignment. It was written there that we had stainless steel. And the diameter was 5.5, and we had an insulation thickness of 0.1 9, and we had 4 wall ties per square meter. And again, we go to DS 418 to find out. And that's here, correction for ties. And here we have this table where we have stainless steel here. We have the diameter, and then we go all the way over to 4 square meters per square meter, and we have 2 in or 200 millimeters of insulation, so 0.2, or we have nearly, so we round it up, and that gives us a correction of 0.005. So we go back and we write that here, and then we can add the uncorrected U value, which was 0. Plus the 0 for the air gaps, plus the wall size 0.005, and that gives us a corrected U value of 0.164. So this is the U1. So now, now we need to calculate U2. So we go to a new schedule here, and I draw again up the construction. We have the brickwork on the outside, and I have the light clinger on the inside. I'm sorry for the drawing. And I have insulation here in the co-bridge, and we have the window here. So where we are looking is now here U2. So again, first we meet is I. So we cross up here and write I. So 0.13. Then the next we meet is the light clinger. And that had a diameter of 0.27. And we had a lambda value of 0.17. So that gives us a resistance of 1.588. And then we have the insulation. And that had a thickness of 30 millimeters to 0.03, and a lambda value of 0.036, and that was given in the assignment. So that is a resistance of 0.8833. And then we have the brick, and the dimension of the brick was 0.108, and the lambda value for that same as before, but we just go back and check. So brickwork, density of 1600, going all the way to external, so 0.63. The resistance, D divided by lambda, is 0.171. Then we have the surface resistance on the outside, RSE, which is 0.04. And then we add all these resistance together, and that is 2.7 3.62, and then the U value is 1 divided by 2.762, which will give 0.362. And then we have the corrections, and we are in level 0 again here, so no corrections for that, and we don't have wall ties in the core bridge, so therefore that goes out. So that gives us the U2, the corrected one, that would be 0.362. So now we have the two U values. What we need to do now is that we need to find what is the liner loss, the psi k, and that we're going to look up in DS418. So we go to DS418, go to table of content, and then we'll find down here we have the psi k. So that is the co-bridge liner losses that we find here. So go to page 27, and then we go down to the table here. And what we have is that we have 30 millimeters of insulation in the core bridge. We have an outer leaf of tiles, and we have an inner leaf of lightweight concrete. So that means we get down here. So that means that the liner loss will be 0. So if we go back and write that here, that the psi k will be 0 according to DS 418 table 671. So now we have U1, U2, and psi k. Now we need to calculate the areas. And if we look at the drawings, then I need the area of A1, so that's how much we have of U1, and the area of U2, that's how much area we have of the core bridge, and then we need to have the length of the liner loss. So the way I would do it is I would first find actually the area of the window, and then I'll find the area of the core bridge, and then I'll find the area of the whole wall without or with the windows and core bridges, and subtract these from it to get U1. So first I'll go back. The area of the window, that is the height that we have of the window, and we have the width of the window over here. So it's 1.33 times 0.91, and then I have 4 windows in this example house here, and that gives an area of 4.84 square meters. Then I want to find or calculate A2, which is the core bridge. And if I make a small drawing of the core bridge, we have here the window, and then we have the core bridge here at the side. And I put the measurement, the height of the window was 1.33, and then we have the core bridge height is 0.12, and then also here the core bridge there is also 0.12, and the length of the window, that was 0.91, and this part here is also 0.12. So first I'll calculate the side of the window and then the top of the core bridge. So A1, that would be 1.33 plus 0.12 times then the width of it, which is 0.12 also, and then I have 2 of these on each side, plus then the top part of the code bridge, which was the height of it, 0.12, times the length of it was 0.91. And then we have 4 of those, so we times it by 4. And that gives us a code bridge area of 1.829 square meters. So now we just need to calculate A1, and that's the main construction that we have. And what I do is I take the whole area of the wall and subtract the windows and the code bridges. So take the height of the whole wall, and that's from top floor to top insulation in the roof. And that is determined in the chapter for areas in DS 418. So 2.785 times the perimeter, and that's external, so it's 4 plus 4 plus 5 plus 5. So 18 meters around this building, minus the area for the window, which was 4.84, and then also minus the code bridge, which was 1.829, and that gives an area of the main wall of 43.46 square meters. And then normally I wouldn't calculate LK because psi k was 0, but now I'll just do it so you can see what is LK. And LK is the part that we have here. So the length between the two thicknesses of insulation. So that would be the height 1.33 plus 0.12, and then we have 2 of these heights plus the top part, which is 0.12 plus 0.91 plus the code bridge again 0.12. So the length of the code bridge, that would be 16.2 meters. And now we have all the different figures, so we can fill out the formula. I'll write the formula again. We have U wall here, the final U value for the wall, that would be U1 times A1 plus U2 times A2 plus psi k, line loss times the length, divided by the total area A1 plus A2. This goes out, of course, because this is 0, so I don't need to put it in to the formula. So we have U1 was 0.18 times the area was 43.46 times the U value for U2 was 0.41 times the area, which was 1.829, divided by the total area, which was 43.46 plus 1.829. And that gives a final U value of 0.189, and we round it up to 0.19 because in the building regulation we only have 2 decimals, and that is in watt per square meter. Kelvin. So this is how you calculate a U value when you have a construction where you have a cold bridge. So hope this can help you when you're going to calculate the U value for your heavy external wall in your semester project. Bye for now.